Okay, class. So last time we talked about using a periodic table to figure out electron configuration, which was so easy. You have a periodic table, you can label it, and then you can figure out the electron configuration using periodic table. And the nice thing about it is that the way the periodic table is set up, it will also take care of all those crossovers for you. So as soon as you get a periodic table on the exam, so write down this is S, right? This is a P, this is a D, this is the F. You should do that. S starts from the first level. So 1, 2, 3, 4, 5, 6, 7. The P starts from the second energy level. So 2, 3, 4, 5, 6. D starts from the third energy level. So 3, 4, 5, 6. F orbital starts from the fourth energy level. So 4 and 5. As soon as you get this on the exam, you write this down. All right, so far so good. Now there are, the other thing I mentioned to you last time, pay attention to when you get to 6 and 7 row, you have to be careful because as we did last time, 56, 57, 56, 55, 56, 57, and then whoa, it jumps to 72, so you have to come down here. Same here, 87, 88, 89, whoa, is 1 or 2 after that, you have to come down here. So be careful with these two, and then beside that, it's pretty simple. Hopefully you guys were able to do some practice with this. Now, there are one more thing we need to know about exceptions. And that's what I'm going to go over today. Before I do that, what I want you to do, I want you to pause my video, you can do that, and write the abbreviated electron configuration for me for copper. For copper, write the abbreviated electron configuration. So copper, I'm going to go back here. Copper is right here. Where is my copper? Right here. So the last noble gas this is copper. The last noble gas is argon, and since the last noble gas will be argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I would get, argon is the last noble gas, and from argon I get 4s2 to 3d9, and that's the electron configuration you get. Now let's talk about this. So it ends with a d orbital, right? Ends with a d orbital. How many rooms do we have in a d orbital? If you remember, in a d orbital, we have 5 rooms. 1, 2, 3, 4, 5. We have 5 d orbitals. Now here, in a d orbitals, how many electrons do I have? I have 9 electrons, right? We're going to put these 9 electrons in a d orbital. Oh, what did it just do? Let's do this. So I want to put the 9 electrons in a d orbital. I go 1, 2, 3, 4, 5. Now I go back. 6, 7, 8, 9. You're going to put 1 in each one, and then you go back and double up. Okay? Now, if you look at this, copper is so close to having a full subshell. It only needs one more, so it would be a full subshell. Now, here's the thing in chemistry, is elements would be more stable if they are filled or half-filled d subshells. So their d subshells would be, if it's completely full or is half-filled, is more stable because it looks more attractive. We talked about this. Nature wants to look attractive. Now, what does that mean here? So here, copper is almost attractive, but not quite there, right? So how do I make copper more attractive? to make copper more attractive, it would be more attractive if I could add one more electrons over here. If I add one more electrons over here, it's going to be a lot more attractive or more stable. So it's worth it to spend energy and get one electrons from the s orbital to make the d to be a full d subshell. I'm going to repeat it again. So it's worth it to spend the energy and get one electron from the s orbital. So you end up having a full d subshell. So your d orbitals is filled. In that case, what argon electron configuration is 4s1 and 3d10. I borrowed this one electron from the s orbital. So that is the exception on a periodic table. Because if you just get one more, it's going to look attractive. Now, let's go back to the periodic table. So that was the case for copper over here. Now, Ag is in the same situation. If he has one more, it's going to be a full d subshell. So it would borrow one from the s orbital, so it would have a complete d. Au also in the same boat. So all of this, what they're going to do, they're going to take one from the s, so they will end up having s to be 1 and then d to be 10. And that would be stable. That would be attractive. Okay. Now, the next thing that I want you to do, I want you to write. Okay. Now, the next thing I want you to do, I want you to write the abbreviated electron configuration for chromium. Before you do that, I want to explain this one more time. So, copper, silver, and gold, they are the exception because they're so close. If they have one more electron, these are all D9, D9, D9. If they have one more electron, they're going to be D10, and that's attractive. That's more stable because it's completely full. It looks better, right? We saw it over here. It looks so much better when it's a full shell. So because of that, they will borrow one from the s orbital. So all of those would be S1 and then D10. Now what I want you to do to write down the abbreviated electron configuration for chromium. Chromium is right here. Okay, you can pause me, definitely pause me and do that. So, I ask you to do chromium. Chromium, the last noble gas is argon, 4s2, 3d4. You probably know where I'm going with that. Okay, the same as before. So here we have the d orbital, right? And then this one has 4 electrons. I'm going to draw it out. So d orbital has 1, 2, 3, 4, 5 orbitals. We have 5 rooms, 5 orbitals. 1, 2, 3, 4. Probably see where I'm going with that, right? We say it's more stable. Is it filled or half-filled? These subshells. So this one is almost attractive. It's going to be more attractive if it has one more. So it was worth it to spend the energy to get one electron from the s orbital, so you end up having a half-filled subshell. If it does that, so you just want one more. You will just want one more. So the actual electron configuration for chromium is argon 4s2 3d5. These are the exceptions. Let's go back to the periodic table. So, chromium, also molybdenum, the same thing. What they're going to do, they're going to borrow one from the S, so you end up having 5D. What we want half full or completely full. That's what we want. So these are the exceptions on the periodic table. Now you might ask, how come I didn't circle tungsten? Tungsten does not follow this. because it would cost way too much energy, because now we have to worry about the f orbitals. So because of that, tungsten is not enough energy for tungsten to do this. So the exception would be chromium, molybdenum, copper, silver, and gold, but tungsten does not do that. It would cost too much energy for it, because it would have to go down to the f orbitals. All right, so these are the exceptions that I want you to know on a periodic table. Now, the next thing we're going to do, and we really haven't talked about this, we want to talk about quantum numbers. We went over the quantum numbers, and we figured out what each number means. But now we're going to see how you would find out the quantum number for each element. Now, before we do that, remember the quantum numbers are N, L, M sub L, and M sub S in this order. Now let's go to oxygen. What I want you to do, write down the full electron configuration for oxygen. Pause me, I won't take it personal. Write down the full electron configuration for oxygen. 1s2, 2s2, 2p4. Now, when you write quantum numbers, I need you to remember this. Quantum number is for the last electrons you put down. I'm actually going to write this down. It's for the last electron you put down. Okay? Now, let's finish this. So this is oxygen. Oxygen, this is the last orbital. Do you guys agree? This is the last orbital. We end with 2p4, last orbital. How many electrons in the last orbital? I have 4 electrons in the last orbital. Last orbital is p. P has how many rooms? 1, 2, 3. P has 3 rooms. And remember, we said because it's quantum number, you have to put a number for everything. 0 plus 1 minus 1. So 4 electrons. Let's do this. 1, 2, 3, 4. Last orbital is p. I put 3. You have 3 p orbitals, and there's 3 different orientation. 0 plus 1 minus 1. I put down the electrons. What did I say up here? I said quantum number is for the last electrons you put down. Which one was the last electrons I put down? This one right here. That was the last electrons I put down. Okay? So, we are going to write down quantum numbers for oxygen. Again, quantum numbers in this order is always N, L, M sub L, and M sub L, S. So, you tell me, what is my N for the last, and also remember, so this was 2p, right? This was in a 2p orbital, because the last one was 2p4, because it was 2p4. Okay, what is my N? Which energy level am I? 2. I'm in the second energy level. Okay, what is my L? And if you remember what L is, L means S, P, D, or F. Do you agree? So L means it was a shape, S, P, D, or F. But we have quantum numbers, so we have to apply a number to everything. So they said S is 0, P is 1, D is 2, F is 3. Because quantum numbers, we have to assign a number to all of them. So L, and again, L means do we have S, P, D, or F? Which one do you have? We have P here. P is 1. We use quantum number 1 for P. Okay, so P would be 1, so L would be 1. Now, M sub L is the orientation, right? So M sub L, if you remember, these are M sub L. The last electron is in -1 M sub L. That's the orientation. So remember, the M sub L is the orientation. So it's going to be -1. Now the last one, m sub s was the spin. Is it up or is it down? Is down. And if you remember, if the spin is up, you're plus half. If the spin is down, is minus half. What are we here? The spin is down, so it's minus half. Okay, so quantum number is for the last electrons you put down. You need to remember that. It's for the last electrons you put down. The last electrons you put down here is this one right here. Is NL, M sub L, M sub N. S. N is your energy level. I'm in the second energy level. The last electrons I put down. L means do you have S, P, D, or F? Which of these apartments do you have? This one is in a P apartment. We have to assign a number for quantum number. Randomly, we said P is always 1. So we put 1 here. M sub L is the orientation. This one is right here. Is in -1. And is it up or down? That's the spin. Up would be plus half. Down, which is this is down, would be minus half. And this is my quantum number. Okay. I'm going to... Now, the next thing I want you to do, I'm actually going to give you a take-home problem and end this video over here. I'll make it a little shorter video. Here's going to be your take-home problem. You ready? What I want you to do the quantum number. I want you to do, this is your take-home. And you thought you would be done with take-home since you're home all the time. No way. Quantum number. And remember, the quantum number is always NL, M sub L, M sub S, in that order. Do the quantum number for potassium and for phosphorus. Do the quantum number for potassium and for phosphorus. And we go over that next time. Alright, nice job. Keep it up.